Composition of real-valued functions. Hello, everyone. Let's begin our lesson on the composition of real-valued functions. To start, let's look back at where we just came from. In the previous subsection, we explored the concept of function composition using discrete sets, where we worked with specific, individual points. However, as we move forward, you will find that in most high school mathematics problems, we deal with real-valued functions. Now, to be clear, these are functions where both the domain, which is our input, and the codomain, which is our output, are sets of real numbers, often represented by the symbol r. The key difference here is that these functions are defined by algebraic expressions, essentially formulas, rather than just a simple list of ordered pairs. Over the next few slides, we will learn how to use these algebraic expressions to create a chain of operations. Understanding the concept. Now that we have established that we are working with real-valued functions rather than discrete sets, let's dive into the actual concept of composition. When we compose two real-valued functions, such as f of x and g of x, we are essentially creating a chain of operations. To find the composition, which is denoted as g circle f of x, we calculate g of f of x. To understand this conceptually, think of it as a sequence. The output produced by the function f becomes the immediate input for the function g. In practical terms, this means that instead of plugging a specific number into g, we take the entire algebraic expression of f of x and substitute it into every instance of x within the expression of g of x. This conceptual understanding is crucial, as it leads us directly into the formal step-by-step procedure we will discuss in the next slide. Step-by-step procedure for composition. Now that we have established the conceptual framework of function composition as a chain of operations, let us walk through the precise, step-by-step procedure you should follow when solving these problems. First, you must identify the inner function. When you see the notation g circle f of x, the function f of x is the inner function. This is the function that will be applied to the input first. Second, identify the outer function. In the same expression, g circle f of x, the function g of x is the outer function. This function acts upon the result produced by the inner function. Third, we move to the substitution phase. Begin by writing down the algebraic expression for the outer function, g of x. However, instead of writing the variable x, replace every single instance of x with a set of empty parentheses. This ensures that you maintain the correct order of operations. Fourth, you will insert the inner function. Take the entire algebraic expression for f of x and place it inside each of those parentheses you just created. Finally, the last step is simplification. Depending on the functions involved, you will use algebraic rules, such as expanding binomials, factoring, or applying trigonometric identities, to simplify the expression into its most concise form. Once you are comfortable with this mechanical process, we will look at a real-world analogy in the next slide to help you visualize why this sequence is so important. Real-world analogy, the multi-stage process. Now that we have covered the technical step-by-step procedure for composition, let us look at a real-world analogy to help you visualize the conceptual flow of this process. Imagine a manufacturing process used to create a product. First, consider stage 1, which we can represent as function f. In this stage, raw material is processed into a semi-finished part. The output of this first stage is the semi-finished part. Next, we move to stage 2, which represents function g in this stage. The semi-finished part is painted and polished. It is important to note that the input for this stage is specifically the semi-finished part that was produced by stage 1. The final finished product is the result of the composition, g composed with f of the raw material. This analogy illustrates a critical rule of function composition. You cannot paint the product in stage 2 until the raw material has first been processed in stage 1. In mathematical terms, the inner function must always be evaluated first before its result is passed into the outer function. With this conceptual framework in mind, let us now proceed to the next slide, where we will apply these principles to some concrete worked examples. Worked examples. Now that we have discussed the theoretical concept and the step-by-step procedure for composing functions, let us apply this knowledge to some worked examples to see how it works in practice. Let us begin with example 1, which focuses on algebraic functions. We are given two functions, f of x equals 2x plus 3 and g of x equals x squared minus 1. Our goal is to find the composition of g and f of x. Following the procedure we established in the previous slide, we start with step 1, identifying the functions. In the expression g composed with f of x, the function f of x is our inner function, which is 2x plus 3, and g of x is our outer function, which is x squared minus 1. In step 2, we set up the composition. This means we are looking for g of f of x as we discussed earlier. This creates a chain where the output of f becomes the input for g. Moving to step 3, we perform the substitution. Since the outer function g of x is x squared minus 1, we replace every instance of x in that expression with the entire expression for f of x. This gives us the quantity 2x plus 3 squared minus 1. Please notice how I used parentheses here. As we will see in the next slide, forgetting these is a very common mistake. Finally, in step 4, we simplify the expression. First, we expand the square of the binomial. 2x plus 3 squared becomes 4x squared plus 12x plus 9. Then, we subtract 1 from that result. This leaves us with our final answer. The composition of g and f of x equals 4x squared plus 12x plus 8. Now let us look at example 2, which involves a combination of trigonometric and algebraic functions. Here, f of x equals sine of x, and g of x equals 3x plus pi over 2. This time, we are asked to find the composition of f and g of x. Again, we start by identifying the functions. Notice that the order has changed. In f composed with g of x is now the inner function, 3x plus pi over 2, and f of x is the outer function, sine of x. For step 2, we set up the composition as f of g of x. In step 3, we substitute the inner function into the outer function. Since f of x is sine of x, we replace x with the expression for g of x. This results in sine of the quantity 3x plus pi over 2. For the final step, we simplify using trigonometric identities. Using the identity that states sine of theta plus pi over 2 equals cosine of theta, we can simplify our expression. Therefore, the final result is that the composition of f and g of x equals cosine of 3x. These examples demonstrate how the process remains the same regardless of the type of function, provided you correctly identify the inner and outer functions and substitute carefully. In the next slide, we will discuss some common pitfalls to ensure you avoid the mistakes many students make during this process. Common mistakes to avoid. Now that we have walked through the step-by-step procedure and seen some worked examples, it is important to discuss some common pitfalls to ensure you avoid these mistakes in your assignments and exams. First, let's talk about the order of composition. A very common error is calculating f composed with g of x when the problem actually asks for g composed with f of x. To avoid this, always refer back to the rule we established. The function written on the right is the inner function, and it is always the one applied first. Next, please be mindful of your notation, specifically regarding parentheses. When you are substituting the inner function into the outer function, it is easy to forget to use parentheses. For instance, if g of x is x squared and f of x is x plus 1, you must write the composition as the quantity x plus 1, all squared. If you omit the parentheses and write x plus 1 squared, you are only squaring the number 1, which will lead to an incorrect answer. Always enclose the entire inner expression in parentheses during substitution. Finally, it is crucial not to confuse function composition with multiplication. The notation g composed with f of x is not the same as g of x multiplied by f of x as we discussed in our manufacturing analogy. Composition is about nesting functions, creating a chain where one output becomes the next input. Multiplication, on the other hand, is simply taking the two separate outputs and multiplying them together. Keep these three warnings in mind as we move forward to our final summary of the key takeaways. Key takeaways. To wrap up our lesson on the composition of real-valued functions, let's review the key takeaways to ensure you have a solid grasp of the concept. First, let's revisit the formal definition. The composition of g and f of x, denoted as g circle f of x, is defined as g of f of x. Regarding the process, remember the chain concept and the manufacturing analogy we discussed earlier. The output produced by the inner function serves as the direct input for the outer function. As we saw in our step-by-step procedure, substitution is key. You must replace the variable in the outer function with the entire algebraic expression of the inner function. Be especially mindful here to use parentheses, as we noted in the common mistakes section, to ensure your calculations remain accurate. Finally, always remember to simplify your final expression. Whether you are using algebraic expansion or trigonometric identities, as demonstrated in our worked examples, simplifying your answer is the final and essential step in the process.